the topic is acids and bases, right? So in my textbook, chapter 14, 15 cover acids and bases and a special topic of equilibrium. Yours has parts of chapter 17 and 16 covering the same material. So I'm going to sort of blend these two PowerPoints together. I'll share the first one. Let's see, where's my share thing? Here it is. Share. And then I'll get chapter 14 first. Here we go. And let's make a slideshow out of it. There we go. All right. So we're going to use topics that we've covered in equilibrium to help us understand acids and bases. But first, of course, we need a definition. What do we mean by acid bases? There are basically three definitions that inform the concepts of acids and bases. The earliest one was Arrhenius, and he simply defined an acid as anything that in aqueous solution would produce protons. And for most isotopes of hydrogen, if you strip the one electron that it has, then you get a positive hydrogen, which is the same thing as a proton, because that's all it's got going for it in the nucleus. So that's why we refer to them interchangeably as hydrogen ions or protons. But that's an acid, and a base will produce hydroxyls in aqueous solution. So that means that if it's an acid, this has to be part of the molecule. If it's a base, that has to be part of the molecule. For example, hydrogen chloride, when you dissolve it in water, it completely dissociates into hydrogen ions and chloride ions. Sodium hydroxide is an example. If you put sodium hydroxide in water, then it will dissociate completely into sodium ions and hydroxyl ions. That's an Arrhenius acid-base definition. Later, actually two people independently, Bronsted and Lowry, noticed that they could measure acidity or basicity of a solution, and the source, particularly of the basicity, the source of the basicity did not have hydroxyls in the molecule itself. So they had to modify their definition. For example, if you take ammonia and dissolve it in water, it will produce hydroxyl ions. Well, where'd they come from? Well, in this case, they came from water. What happens is the ammonia strips one proton off of that water molecule, right? It's got two hydrogens. Leave one hydrogen here. You just take the proton off and you leave the electron behind. So it becomes the charge. And you attach it to that ammonia with an extra hydrogen and the plus charge. So that will give you a basic solution without the source of hydroxyls in the molecule itself. So Bronsted and Lowry modified the definition, and they said that a base is an acid is a proton donor. Anything that will give up a proton. And a base is a proton acceptor. So the definition didn't change much for acids, but it did for bases. Anything that will accept a proton is a base. that also introduces the possibility for acid-base compounds or acid-base reactions in non-aqueous solutions. Because if you can accept a proton as a base, it doesn't have to come from water. It can come from anything. So you could put, in this case, you could put ammonia in some other solvent, and as long as it can strip a proton off of that solvent, then it can act as a base. Okay, those are the first two. Arrhenius definition covers over 90% of acid bases in aqueous solutions, and that's where we're primarily interested, because all biochemical reactions of interest to living systems are aqueous based. Bronsted-Lowry's, they're sort of drifting more toward chemistry than biology. And then there's a third definition that we'll cover a little bit later. It's called the Lewis acid, Lewis base. And I'll save that one till later. We'll give you that definition. But for now, we're focused on protons and hydroxyls. All right, so in a reaction, you have an acid. If you have an acid that's reacting, you'll also have a base. It's like they come in pairs. So in this case, I'm going to try to save time by just using the slides. In this case, we're saying HCl, and this is, we assume this is aqueous solution because there's water, transfers its proton to the water molecule. And as a consequence, we have the chloride ion left over, plus we have this species here, H3O+. That has a special name. It's called a hydronium ion. And in fact, even though we write reactions, I said I wanted to do this, but I have to. Even though we write reactions like this, in aqueous solution, what actually happens, protons never exist as separate entities in any chemical environment. They're always transferred from one place to another. So what actually happens is that reaction. Where we have this left over plus the hydronium. Now by definition, this is your acid. Right? It's the proton donor. The proton acceptor is the water molecule. That's the base. So the donor, acceptor, acid base. Now, when we strip the proton off of this acid, it gives us this. Now, what could that do? Well, this in any other environment could be a proton acceptor, right? But we can't just call this a base, right? Not in the same reaction, because the terminology would get confusing. So this is the conjugate base of this acid. And you can probably see where I'm going with this. That makes this the conjugate acid of that base. Okay? Terminology. And it's just a little animation here. There's a tug of war going on for that proton. This reaction can also happen between water molecules. If you have pure water, you can have a reaction where a proton is transferred from one molecule to the other. So we have this one plus this one. Okay? So one of these is the acid and the other one's the base. And that's what this bottom diagram is showing. Okay, so we've already defined these things. More terminology. When we describe a strong acid, what we mean is that in terms of equilibrium, when the acid dissociates, the equilibrium lies far to the right. It may not be complete, it may not be 100%, but it's a very large number, right? So that means the equilibrium would shift far to the right. That's a strong acid. Doesn't matter what the concentration is, right? It's a strong acid. A weak acid, the equilibrium lies far to the left, right? So it's undissociated. A perfect example of that one is acetic acid, right? Vinegar. Right? When you put that in water, then you do get some transfer. This proton transfers there. And you have the acetate ion. Oops, there you go. This would be a weak acid because most of the acetic acid remains neutral. In other words, it's still got its proton. And if we write an equilibrium expression for that, what would that look like? Right, it would be a K. And remember, when I first introduced the topic of equilibrium, the subscript on the K has special meaning in some cases. In this case, we would say K sub A for K for acid. And the equilibrium then would be this one right? It's only got first power, and then that one, divided by this one, and that's it, correct? Pure liquids don't count. Solids and pure liquids don't count. So this would be the equilibrium expression for that reaction. It's also an acid equilibrium expression. And the value for this one is about 1.7 times 10 to the minus 5. Right? So that very small number, 10 to the minus 5, means that most of it is over here. Okay? All right. So that's now. The definition of strong acid, weak acid is in terms of equilibrium. Remember when we discussed equilibrium, I said that there's a difference between the equilibrium constant, that value, which is constant for as long as the temperature doesn't change, and the equilibrium position. The equilibrium position takes into account the starting point concentrations and says, okay, that's with this concentration, that's how much product you'll have. Right? And that can change depending on where your starting point is. So the aggressiveness of an acid depends upon how many of these, how many hydroniums there are, how many protons are released, absolute amount. So if you have a very low concentration of this weak acid, then you won't have very many of those. But if you have a high concentration of the acetic acid to begin with, then the equilibrium still lies far to the left, but with a high concentration, you have a whole lot of these. So a high concentration can make a very corrosive, aggressive acid, even if it's weak. And in fact, we used to buy bottles of acetic acid to use in various chemical reactions. That was 100% acetic acid. It was a liquid. And they called it glacial acetic acid. But it's 100%. And it's very corrosive. In addition to that, of course, that's an organic molecule, right? You mix organics with oxygen in a spark or ignition source, and they will burn. This acid will burn. So you don't want to store that acid in concentrated form with other sources or other acids or bases, for that matter, any materials that can act as an oxidizing agent. Not just oxygen, but nitric acid, sulfuric acid, all those will react with this violently, and it will oxidize, it will burn. Okay, so I'm taking too much time here. Let me move ahead. So for a strong acid, you get complete dissociation going from this side to that side. Almost 100%. And for some calculations, that's a valid assumption. Pardon me. And then for, you can say the same thing for bases. I mean, we provided this definition for acids, but the strength concept works for acids and bases. For bases, you can say that for a strong base, the equilibrium lies far to the right. So if you combined ammonia and water, that's not a good example because ammonia is a weak base. But if you had a strong base like sodium hydroxide, then it would completely dissociate into sodium and hydroxyl ions and end up on the right-hand side. Weak bases like ammonia, it's mostly ammonia, it's 98% ammonia, even dissolved in water. Okay, so this is just a compilation of everything we've said so far. The Ka value for a strong acid is very large, for a weak acid is very small. And all the assumptions, all the conclusions that can be drawn from that are the same as if we were talking about equilibrium in any type of reaction. So that's nothing special in terms of equilibrium. Okay. So here we have what's called auto-ionization, self-ionization, which means if you have the pure substance, in this case water, you can get a proton transfer from one water molecule to the other, right? And this is also called amphoteric. Right? So 6 of one, half a dozen of the other. Ammonia will do the same thing. It will also transfer a proton in pure ammonia. Right? Where would you find that? Well, the best place to find pure ammonia is either in a chemical plant or on a farm. Nitrogen fertilizer delivered as anhydrous ammonia. That just means that there's no water in it, and it's virtually 100% ammonia. So some farmers have the equipment where they can receive a shipment of anhydrous ammonia in a stainless steel tank. It has to be stainless steel, and their equipment will allow them to inject ammonia into the ground. It has to be injected into the ground because as soon as it hits the air, as soon as the pressure's off, it will immediately turn from a liquid into a gas. And if you don't put it down in the ground, it won't stay put. Okay, so that's auto-ionization. There's the other term, amphoteric. It can behave as an acid or as a base. Right? The Bronsted-Lowry definition says all you need to say about an acid is it donates a proton. And all you have to say about a base is it accepts a proton. So that being said, pure liquid water, some of the water molecules act like acids and some of them act like bases. And if you write the K value for that reaction, where you have water yields hydronium plus hydroxyl, right? You just transfer a proton from one side to the other. Then you can write an equilibrium expression for this equation, right? And we give it a special subscript W. And we just say that right there. Pardon me. All right, notice that here they've written it with protons only. That's a convenience. As long as you recognize that it's really hydronium ions, the concentration is the same, whether it's hydronium or protons. And we write it like this because, why? These two are pure liquids, right? So they're not part of the expression. They don't count. Their concentrations do not change significantly. They're like 45 molar, right? So you take just a few of those, right? The concentration doesn't change. That's why liquids aren't included. But this expression has a Kw value of 1 times 10 to the minus 14, which means what? It's still mostly liquid. They're just tiny amounts of the hydronium and the hydroxyl produced by this autoionization. Now, this at 25 degrees, right? In aqueous solutions of any kind, no matter what you put in them, this reaction is always there. It's always occurring. And these conditions must be satisfied no matter what else you put in there. You have to consider that. It may be insignificant compared to the reaction that you're interested in aqueous solution, but you always have to think about it in terms of where the reaction is going and what it produces as a consequence. There are some other things that we can say about this, right? If we know this in pure water is the relationship, and that's the product, what's the concentration of this one? And what's the concentration of that one? They come from the same source, right? So half of it's going to be here and half of it's going to be there. That means this one is 1 times 10 to the minus 7. And this one is 1 times 10 to the minus 7. We could prove it with an ice table, right? But that's a fact. In pure water, that's the concentration of hydroniums, and this is the concentration of hydroxyls. Now, what does that mean? Well, in pure water, these will both be equal, and that means you have a neutral solution. There's no excess of either one, right? So it's not favoring an acid, it's not favoring a base. So that's neutral right there. But if you augment that solution with an external source of protons, Then it enters into this reaction, and if this is decreased, or increased, excuse me, increased to 10 to the minus 6th, right, instead of minus 7, right, that's an increase, minus 7 to minus 6. Then this one has to decrease in order to maintain that value, because this is an equilibrium constant. It has to be constant. So that means this one has to go to 1 times 10 to the minus 8. See that? You can go the other direction, right? Increase the hydroxyls by adding extra hydroxyls into solution. Then the equilibrium is going to shift to be sure that that constant is honored in the calculation. So that's why if you have more hydrogen ions, which is hydroniums, more hydrogen ions than hydroxyls, you have an acidic solution, and the other way around is a basic solution. Okay, I mentioned this earlier. One's an acid, one's a base. The acid gives up its proton and becomes a conjugate base. And the base accepts a proton, becomes a conjugate acid. So in the equilibrium sense, this could go back the other direction, right? This becomes the acid and donates a proton to this conjugate base. Now we got the conjugate base and the conjugate, and the base and the acid reconstituted. And this equilibrium is going on all the time. So that would be your K expression, the Ka expression for this. So if the equilibrium lies far to the right, the value of Ka is very large, greater than 1. If the Ka is small, the equilibrium lies to the left and less than 1. Notice also that when we write the K equilibrium expression for an acid, or a base for that matter, we'll talk about bases in a minute, but for acids, notice that the reaction is always expressed in terms of one proton transfer only. Right? So what do you do with polyprotic, we say, polyprotic acids? For instance, let's say sulfuric acid. Oops, sorry. That's not right. There. And for convenience, let's just do away with the water. Let's just put the water right here in that. Right, so when it dissociates, it would produce a proton and, right, and that ion, hydrogen sulfate ion, only one proton at a time. So the K for this one, in fact, we put a subscript on a subscript. The Ka1, which means the first proton, would be like that. Now, why did I include this one over here? Because it's not pure liquid. It's an aqueous solution, so we do include it. Now, what would we do for the second proton? Well, acids do dissociate one proton at a time. So now you would take this one and dissociate the second proton. So if you did that, what would it look like? The Ka2 then would be, this one would be in the denominator. Oops, that's supposed to be 4. HSO4, and then this would be SO4 2 minus. Okay, so the second proton dissociation has its own K value. All right, so that's important. Whenever acids dissociate, they do so one proton at a time. And they each have their own unique equilibrium expression and constant. All right. You could use that same logic for phosphoric acid, which has 3 protons. You'd have an expression for each one. First, second, third, dissociation, each have their own dissociation constant. So, if we talk about this acid in solution, reacting with water to produce a hydronium and this free anion, what do we mean when we say if water is a better base than the A minus? Right? So we would have to, it's instructive to write the expression. What do we mean by base? Well, if water is a base, that means water accepts a proton. Okay? If A minus is viewed as a base, it accepts a proton and produces the original acid. So when we say, if we make comparisons about which is a better base, what we mean is which one attracts protons more strongly. Right? So if water is a better base than A minus, that means this one tends to produce more of that than this one produces of that. So it favors the production of the hydronium. Right? So if water is a better base than A minus, the reaction will be on this side over here. Right? Water accepts a proton versus A minus taking a proton from the hydronium and making HA. Okay? So, there's another concept. If HA is a strong acid, what does that mean about A minus? A minus is a weak base. So the conjugate base of a strong acid is always weak. And you may see where I'm going with this. If it's a weak acid produces a strong conjugate base. It all has to do with the idea of attraction of protons. If there's very low attraction to a proton, that makes a weak base. Well, a strong acid wants to give up that proton badly. It wants to get rid of that proton so bad it won't take it back. Right? So a strong acid makes a weak base. And vice versa. A weak acid makes a strong base. And that's important to concept for understanding how equilibriums can shift when you're talking about acids and bases. All right. So for this situation, 1 molar solution of HCl, we assume that's aqueous solution. That's pretty high concentration. So let's put these in order. Strongest to weakest base in a 1 molar solution of HCl. Right? So which would be, when you have 3 like this, what I like to do is say, all right, which one's the strongest, which one's the weakest, and then the other one just fits in the middle, right? Okay, so which is the strongest base? The strongest base would come from the weakest acid. And the weakest base would come from the strongest acid. So what's the source? What's the source of this chloride ion? That chloride ion comes from a strong acid, which makes it a weak base. So the chloride would be in base order, right? That's the weakest base. It has the weakest attraction for protons. All right, so which one would be the strongest base? Well, the strongest base, well, it could, we're not given absolute amounts, right? So it's really hard to tell which one is which, water or A minus. But if A minus comes from a weak acid, it's going to make a strong base. The question is it a stronger base than water? Right? So we can make assumptions and we can say this would be the strongest base and water's in the middle. Right? That's one approach. And that may be what they're getting at here. But until you know what the values are for the dissociation constants, the equilibrium constants, you can't say for sure. It could be the other way around. Right? If this is acetic acid, the Ka for acetic acid, like I said before, is 1.7 times 10 to the minus 5. The Kw for water is 1 times 10 to the minus 14. Right? So that's a weaker acid, which makes a much stronger base. So in this case, if the acid is this one, then water would go on this side. But if the Ka for the acid were hydrocyanic acid, I can't remember exactly what it is, but it's probably times 10 to the minus 17 maybe, then it would be the order that we put it in first. So that's really not a good question, is it? It could go one of 2 different ways. But it does offer an opportunity for an explanation. And hopefully will pique your curiosity. How good is chloride as a base? It's horrible. It comes from a strong acid, so chloride is a terrible base. A would be a better base. So here we're assuming, right, that we've got a really weak acid, which makes A an extremely strong base. All right. Now let's consider an alternative. Instead of putting the acid in solution and working from there, let's take the acid and combine the anion, the conjugate base, A minus, with some other cation, in this case sodium. Right? So what happens? Well, all sodium, and this is a salt, all sodium salts dissociate completely in water. Right? So what do they produce? They produce sodium ions and A minus ions in this case. So here you have A minus ions, and now they have an opportunity to interact with Water. Well, if the source of that A minus is a weak acid, so we might say sodium acetate. If the source is a weak acid, that makes A minus a very strong base. Right? So if it's a strong base, what's it going to do? It's going to have a very strong attraction for protons. And if you just put this A minus as the sodium A salt in solution, it will react with water molecules already there and extract a proton from them. So then that base will produce a conjugate acid, HA, which is a weak acid, and hydroxyls. So that being the case, if A minus attracts protons very strongly, then the equilibrium is going to lie to the right over here with the conjugate acid and the hydroxyls base. That means your solution is going to be basic. You're going to produce extra hydroxyls. And the equilibrium will, wrong. That's the way the slide came to me from the publishers. But I discovered that error and said, well, let's make it fun. It's not to the left, it's to the right. Okay. And what does that say about the K value for this reaction? The K is not going to be less than 1. It's going to be greater than 1 because we're favoring products. Okay. Now that brings us to the subject of, we wrote a Ka before, now we can write a Kb. And a Kb for this reaction would be the HA, the hydroxyl, divided by the A minus. So that would be the Kb. Now the temptation is to take the Ka of this acid and just invert the equilibrium expression and call it Kb. But that's not the way it works, right? What would the Ka be for HA? The Ka for HA would be HA on the bottom. Then you would have protons, protons. Right? So this would be reactants. These would be products for the Ka. But for the Kb, notice there's no, you can't just flip this one and call it Kb. It doesn't work that way. So we have to derive, they are related, because they do occur in aqueous solution. These are related, but they're not inverses of one another. You have to define the reaction that occurs in aqueous solution to make the comparison and make the conversion from one to the other, which you can do. And we're going to do in just a second. That means A minus is a strong base because it came from a weak acid. Okay. All right, before we get to the point where we're going to do those conversions, pardon me. You want to go out? Yeah. One, yeah. So before we derive that equation, let's look at some qualitative conclusions that we can draw from what we know so far. We'll come back to this one. Acetic acid and hydrocyanic acid that I mentioned earlier are both weak acids. But hydrocyanic acid is much weaker than acetic acid, which means its equilibrium will be even further to the left as you put it in solution. So now let's arrange the bases, the conjugate bases, from weakest to strongest. All right. So which would be the weakest base? The weakest base in this group would be the one that's derived from the strongest acid. Right. So you just add a proton there. Hydrochloric acid, oh yeah, it's a strong acid. And there's none other that even come close to it. So chloride ion is the weakest base because it comes from the strongest acid. Right? So that's the weakest one. What's the strongest one? The strongest one is going to be Cn minus because it is the weakest acid source in this group, which means it's the strongest base. So we'll put it over here. Right. Now what we have to do is decide what's left, the acetate ion and water. Well, we know that the acetate is 10 to the minus 5 and water is 10 to the minus 14. So water is going to produce a stronger base, hydroxyls, than the acetate. So we would put water here. Water's attraction is 10 to the minus 14. And acetate, I think that's right, based on my reasoning. Let's see. Oh, okay, so it's going to talk about it for us. So the Kw for water is 10 to the minus 14. The Ka for acetic acid, I said 1.7, 1.8. No, very close. The important thing to watch is right here, the power of 10. HCl is a strong acid. HCN is the weakest acid, 10 to the minus 10. Okay, so I was wrong there. 10 to the minus 10th for HCN. So I got it right. It was just I wasn't quite sure. Which means that HCN is a weaker acid than acetic acid. Right? So it's going to be to the right. The base is going to be stronger. The conjugate base is stronger than the conjugate base for acetic acid. And then water, being 10 to the minus 14, is going to be even a weaker base. All right. So what's the value of K for this reaction? Notice what we've got here now is this weak acid and this conjugate base of a weak acid, HF. HF is a weak acid. I know it's in the same family as the chlorine and bromine and so forth, but for reasons that I won't go into now, HF is a weak acid. And the reaction produces Cn minus with a transfer of that proton to the F minus. Right? So what do we need to determine? Well, since protons are being transferred and we were looking at the acceptance, what is the strength of attraction of protons, we're really looking at the base function. So which one is the stronger attractor of protons? Cn minus or F minus? If F minus is stronger, then the equilibrium is going to lie to the right. But if Cn minus is a stronger attractant of protons, the equilibrium is going to lie to the left. I guess we could look at it as acids too. How ready is HCN to give up a proton? And how ready is HF ready? Will it give up a proton? So let's look at this. HCN. HCN is 10 to the minus 10th, right? So it has a very weak proton donation power. But HF has a much stronger donation power. Look at that, 10 to the minus 4th versus 10 to the minus 6th. 6 orders of magnitude stronger, HF. Even though it's weak, right, 10 to the minus 4th is weak. So HF is going to be more prone to give up its proton than HCN is. So that means the reaction will lie to the left. Okay, so you can look at it either way. Cn minus is going to be a stronger base than F minus, which means this one wants to accept a proton, drives it to the left. Or this one wants to give up a proton more strongly, drives it to the left. Either way works. Right? So that's what these statements are saying in the words that I just gave you. Drives the reaction toward HCN, toward the reactants, which means the overall K should be less than 1 because it favors reactants. Now, you can actually calculate the K value for that reaction, but it takes a little extra work. So before we do that, let's figure out how to determine Kb for the conjugate base if we know the Ka for the acid. Right? So here's our acid expression, right? Our generic acid expression. HA dissociates into A minus and H plus, right? And there's the Ka expression, all right? So what if we take A minus independently, add it to water? Don't add it as the acid, add it as the free anion. What's going to happen then? Well, it produces this reaction. It removes a hydrogen from water and leaves the acid and the hydroxyl. So we write the expression for that, right? There's the products divided by the reactant. Water doesn't count because it's a pure liquid. Then what happens if you add those two expressions together? If you add this one together, HA cancels HA because they're on opposite sides of the arrow. A minus cancels A minus because they're on opposite sides of the arrow. So what do you got left? What you have left is H2O dissociates into H plus and OH, right? So what does that look like in terms of the reaction? Well, remember, when you add two reactions together, you multiply the K values. Remember that? Multiply Ka and Kb. But we already know that Kw, and that's what this would be for, dissociation of water, Kw is equal to hydrogen ions plus hydroxyl ions. So Ka times Kb equals Kw. So whenever you have a Ka for an acid, to calculate the Kb, you have to set this product equal to Kw, which is 1 times 10 to the minus 14. Right? So whenever you have Ka times Kb, it's equal to 1 times 10 to the minus 14. So that means if you want to know Kb, Kb is always equal to 10 to the minus 14 divided by Ka. All right? That's how you calculate the Kb for a conjugate reaction from an acid to a base. Or if you know the Kb, that's how you calculate Ka. All right, so now we're going to try to calculate the K for this reaction that we looked at a little earlier. So what we need to do is break this reaction up into two competing reactions and then add them back together, because all together we can't put it back together until we tear it apart. Uh-oh. Am I locked up? There we go. It froze for a minute. So we break the reaction up into two separate reactions, both acid dissociations. HCN produces this, and HF produces that. Okay. We know that the K for HCN is this, and with that value that we picked from a previous slide. So the dissociation of hydrocyanic acid equilibrium gives you this value, and the dissociation of HF gives you this value, right? But we can't add these two back together, right? Because F minus is on the wrong side. So what we have to do is convert this one to a K so that the reaction can be added back together, right? We're going to use Hess's law, except we're not using thermochemistry now, we're using equilibrium. But we can add these equations together once they're in the proper form. So we invert this reaction, and we find that the if we just invert the reaction, right, we don't have to do the KB. But if we flip this reaction and produces this form, then will that add together with this form to give us the original? Well, it looks like it will, right? Protons on either side cancel one another. And then we have HCN on this side, we have F minus on that side, and we have CN minus on this side, and we have HF on that side. So in this case, you do invert. If you flip the reaction, you do invert the K. Right? We're not going for KB here. We're going for the inverse of K. That's why I wrote it this way with that minus. That minus sign means inverse. Now that we know these two, we can add the equations together. We can take this K times that K, and that will give us the K for the combined reaction. All right, so that's add them together, cancel terms from both sides. Now we have the target reaction is confirmed. That means the K for the reaction is we'll multiply the two together plus the modified one, this one times the modified one. And we find that the K is 8.6 times 10 to the minus 7. And we did not have to conduct the experiment. We have to do the reaction and measure it. We can calculate the K for this reaction. Okay. Now let's talk about pH. Let's see, I need to move this back. Looks like it's, hold on a second. Is it drifting? Or did it change? Yeah, I can't even see the whole thing anymore. So something's changed. My zoom level has changed. So I assume everything's still okay. It must have been that glitch I experienced earlier when my screen froze. May have had something to do with the my connection with the Zoom site, because all these video recordings are being streamed to the Zoom servers for recording. I'm not recording on my home computer. So if there's an interruption in the internet service of any kind, then things will look like they freeze up. Hopefully, we're still recording. I better check that too. Hold on a second. Let's go back.
It's showing in the corner of the screen that you are still recording.
Good, thank you.
You're welcome.
Okay, so now we can talk about pH. All right, there was I think it was Danish, could have been Swedish, Danish. His name was Sorensen. Sorensen, I think. Anyway, this scientist was working with living systems, and he wanted to describe the acid conditions surrounding his living systems when he was doing experiments. And he found the scientific notation even was too unwieldy. Right? He didn't want to write out all that stuff. So he invented this conversion. And this is really just simply a conversion of hydrogen ion concentration into some other form that's easier to deal with. And he called it little p, big H, pH. So this pH is simply a transformation of the hydrogen ion concentration. And of course, we know that that's hydronium, but it works better this way because that H is over here. And this just means it's a logarithmic scale. Whatever this concentration is, take the log of it, and this is the common log, right, base 10. It really needs to be base 10 because with scientific notation, then it's easy to get rid of that exponent. So log base 10 of the hydrogen ion concentration, but when you do that, you usually end up with a negative number because these values are so small. That's just the nature of the log transformation. So he put a negative sign in front and made them positive. Right? For instance, if we had, say, hydrogen ion concentration in a neutral solution of water, pure water, would be what? 1 times 10 to the minus 7. So what's the log of that? Well, the way logs work is the number here, the resolution of that term is 10 to the power of what equals this. So this would be 10 to the minus 7 power, right? Oh, no, excuse me. That's what that is. That would be minus 7. Minus 7 would be that term. Right? Because the log of 1 is 0. Plus this one. But he didn't want to use negative numbers either. So that's why he stuck a negative out in front. So what that means is, for pure water, which is neutral, the pH is 7. That's where the neutral pH comes from, 7. And if you increase the concentration, say we went to 6 instead. So that would be minus 6, pH is 6. So if we increase the hydrogen ion concentration, we add a little bit of acid to it, like hydrochloric. Then as the concentration of hydrogen ions increases, the pH decreases, goes from 7 to 6. So the acid part of the scale is less than 7. An extremely acidic solution would be anything around 1 or 2. And that's what you find in your stomach. Hydrochloric acid in your stomach makes the pH between 1 and 2. And basic solutions are greater than 7. Right? The other thing that you might run into, is what do you do if you're conducting a calculation and you need to know significant figures? Right? So in that case, the number of decimal places in the log is equal to the number of significant figures in the original number. So if the significant figures here were like 1.33, times 10 to the minus 6th, then whatever this number is would be the number of decimal places. Well, I don't know what that would be. Maybe 5.65. 2 decimal places. No, excuse me. Actually, it'd be 3. Right? The number of significant figures here would give you 3 decimal places in your calculation. That's just the nature of the log transformation. Okay, so that's pH, but since this is just a mathematical manipulation, right? You can put anything in there, negative log of something, it doesn't matter. In this case, of course, we're talking about hydrogen ion concentration, so pH is that transformation. But suppose you know the hydroxyl concentration, and you don't know the hydrogen ion concentration. What would you call that? That's the POH. Okay? What if you knew the K value and you took the negative log of the K expression here, whatever it happens to be? Then you would have pKa. Right? So you can do this negative log transformation on anything and just precede it with a P. Okay, so I mentioned that already. These are some things that we know roughly the pH of each one, right? Sodium hydroxide is going to be a very high pH. Hydrochloric acid is going to be very low pH. There's battery acid, stomach acid, lemon juice, vinegar in that range. Vinegar is about, that's a good estimate, 3, 3.5. Black coffee is slightly acidic. Milk is just a little bit acidic. Blood is actually basic, right? Well, they teach you in, well, I don't know if you've had anatomy and physiology, but the pH range for a healthy person in their blood is, if I can remember correctly, is 7 point. I can't remember. I think it's 7.25 to 7.35. Something like that. It's slightly basic. And the reason it stays there is because of buffering systems. And we're going to talk about buffers later. I may not be able to talk about them with an audience, but I will record it. Okay. So what's the pH of each of the following solutions? Simple. If this is the hydrogen ion concentration, you just take the negative log of that value, and if it's 1 times 10 to some power, negative power, it's easy. You just take the negative of that power, and you're there. What about this one? If we have POH of 0.040, hydroxyl ion concentration, negative log of that value. Well, this is 4 times 10 to the minus 2, right? So you would take the negative log of that value, and that would give you POH. Or we could go to the expression of the KW, and if KW is 1 times 10 to the minus 14, and that's equal to the hydrogen ion concentration times the hydroxyl ion concentration, 4 times 10 to the minus 2, Then we can solve for the hydrogen ion concentration, which would be 1 times 10 to the minus 4 divided by 4 times 10 to the minus 2. Right? So this would be 1/4, 0.25, and this would be times 10 to the minus 2, which would be 2.5 times 10 to the minus 3. And then you would take the negative log of 2.5 times 10 to the minus 3. That would give you the pH. So if you do that, we find that the pH is 12.6. Right? Take the negative log of that value. How about this one? pH of a solution that is 5.85. Okay, now we're going back the other direction. It's also known as the anti-log. And for common logarithms, right, this is the way the logs are built. If x is equal to the log base 10 of y, that means that y is the x power of 10. Right? So if you know that the pH is 5.85, let's see. Okay. If you know that pH is 5.85, you go back to your expression. That's equal to the negative log of the hydrogen ion concentration. So how are you going to find that from here? Well, first you have to get rid of that negative. So you need negative 5.85 equals the log of hydrogen ion concentration. And the hydrogen ion concentration is equal to 10 to the minus 5.85. So you plug that in your calculator, and you get 1.4 times 10 to the minus 6 molar. Right, that's how you go backwards. So every calculator has LOG on it. So you look for your LOG. There's my LOG. And then somewhere close to that is going to be 10 to the x. That's the anti-log. And that's the one you use, 10 to the x. Okay, so now we're going to relate pH and pOH in a way that simplifies the whole process. Right? We use that hydroxyl ion concentration before and converted it to proton concentration, and then we took the negative log of that. That's the hard way. I'm going to show you the easy way. Remember that Kw is always hydrogen ion hydroxyl's product equals 1 times 10 to the minus 14. Always. In aqueous solution. So if we take the negative log of both sides, which is valid, right? The negative log of a product is what? It's the log of the first term plus the log of the second term. So the log of the first term is negative log of hydrogen ion concentration. The log of the second term is the negative log of hydroxyls. Add those together. So that's minus this, minus that. And then the negative log of Kw is for the other side. So it's a mathematical identity. If you do the same operation on both sides of the equal sign, then you haven't changed the equality. So we're taking the negative log of both sides. And that's what we get to begin with. Okay. So this negative log is going to be that term. This negative log is going to be that term. And we already know what that's going to be, right? 7. And this is plus 7. Well, what's the negative log of this one? 14. Right? Well, this is pH. This is pOH. So pH plus pOH is equal to pKw. And what's pKw? 14. pKw is 14. So 14 equals pH plus pOH. All right. So that means if you know hydroxyl ion concentration, all you have to do is calculate pOH and subtract it from 14 to give you pH. So pH of this one would be, calculate the pH would be 4, subtracted from pOH, which is 14, it gives you pOH of 10. pOH of this one well, you just calculate that one, right? But this one is also, remember we had 12.6, I think it was. We determined pH of that solution to be 12.6. Well, 14 minus that would be 1.4, would be the pOH. So the pH of a solution is 5.85. What's the pOH? You just subtract it from 14. Oh, well, you could do it that way. Actually, calculate the pOH first, right? So we would have 14 minus 5.85, correct? Yep. So that'd be 5, 1, and 5 from 13 is 8. 8.15 is the pOH. And then we say 10 to the minus 8.15 is equal 7.1 times 10 to the minus 9 molar. All these concentrations are in molarity, moles per liter. Okay. So when we've got an acid-base reaction that we need to solve a problem for, there are some steps that can help you avoid some obvious pitfalls. What we have to do when we're talking about acid-base reactions is we've got to identify the major species. That is, those are dominant. And the minor species we can ignore. So what are the major species in the solution? And then you decide what are the reactions that these major species are involved in that solution. Then in addition to that, you look at each one of the reactions and say, does this reaction go to completion? Or is it equilibrium? If it goes to completion, then you let it go, and then you use that information in an equilibrium expression, right? We're interested in the equilibrium expression because if it goes to completion, then there's nothing to worry about. I mean, you just carry it to the completion. Whatever the stoichiometry is, that's your answer. But if we're talking about equilibrium, then we need to take into account these completion reactions and use that information in the equilibrium expression. And then if you're asked, then solve for the pH. So I know that doesn't mean a lot. So let's take this one. Aqueous solution of 2 times 10 to the minus 3rd molar hydrochloric acid. What are the major species? That's it. Why? Because we know that hydrochloric acid is a strong acid. It completely dissociates. So it produces hydrogen ions, chloride ions, and there's always water there, right, in aqueous solution. So what's the pH? Well, this reaction goes to completion, right? So what's the concentration of the hydrogen ions? 1 to 1. 1 mole of hydrogen produced for every mole of HCl. So that means this molarity produces that same molarity for hydrogen ions. So we take the negative log of that value. And there's your pH. This was not an equilibrium expression. How about this one? Similar. HCl doesn't remain. Major species are like before. So all you have to do is take this concentration, calculate the pH. Okay. Was there a question? Oh, this is the question. When nitric acid is added to water, the reaction takes place like this. Nitric acid plus water produces hydronium and nitrate. Goes completely to the right. Notice there's no equilibrium arrow there. Why is this reaction not likely? So we're starting to logically think about what reactions are acceptable. Right? So if we know that this one dissociates completely and goes to this side, that means nitrate is a weak base. If it's a weak base, this reaction will not occur. Nitrate ion will not extract a proton from water. That's why this reaction is discounted. So now we have to think about what reaction actually controls the pH. Right? And when we do that, we have to consider both the acid that we add and the aqueous reaction that's always there, the self-ionization of water. Right? So in that term, what I'm saying is the acid that we add to water stronger than H2O, or is it weaker? If it's weaker than H2O, that means its Ka will be less than 10 to the minus 14. If it is less than 10 to the minus 14, then the reaction that controls the pH is the water reaction. All right. So what's the pH of this solution? Well, nitric is much stronger acid than water, so we can ignore water. We just approach this as if nitric acid is the only producer of protons and calculate it. Major species. Okay, you have this, you have that, you have that. You have none of this. It's not an equilibrium. So we just take the negative log of this value, and that gives us 1.82. So these are steps that you would take in solving an equilibrium and a weak acid equilibrium problem. What are the major species? You need to look at that first. Then you pick the species that can produce hydrogen ions and write the balanced equation for it. Then you decide which equilibrium will dominate in producing protons. There may be more than one reaction you have to consider. Then you write the equilibrium expression for the dominant equilibrium. Then you set up your ice table and decide which X will give you, if you can, decide which X, once you determine it, gives you the exact answer. It's inefficient to assign an X to a value that has to be further calculated to give you the answer. If you can assign X to the answer, that's the way to go. Then once you've determined what the answer is, look to see if the 5% rule is satisfied. Because if you make any assumptions along the way, like we used to with equilibrium, if the X is a lot smaller than the other term, say 10 minus X, if X is really, really, really small, then you can ignore it, and that simplifies the calculation. If you do that, then you better go back and check your 5% rule. and be sure. So then, once you determine what your hydrogen ion concentration is, if the question is, what's the pH? Then calculate the pH. Okay, so let's use this example. We have a 0.8 molar aqueous solution of weak acid. And of hydrocyanic acid, and its Ka value is 6.2 times 10 to the minus 10. Okay, what are the major species in this solution when you add HCN to it? Right? HCN, it's a weak acid, so it's not going to dissociate very much. And water, those are the major species. Just for instruction purposes, why don't we include H plus or CN minus as major species? Because you don't get dissociation. They're not major species. They're very minor species. Simply because HCN has a very small dissociation constant, and in fact, the K value is greater than it is for water. Right? So that means any of the hydrogen ions produced, most of them will be coming from HCN. So not even the hydrogen ions from water will be major species. Right? So what are the reactions that we're interested in? Well, HCN dissociates into protons and cyanide ions with this K. Water dissociates with this one. Remember, water is always there. Well, look at the difference. Which one is going to produce the major share of hydrogen ions? It's this one. So that's the reaction that controls the pH. Oh, that's as far as we were going. Okay, so that's all we wanted to do. Just find out which one controls the pH. We're not going to do any calculations with it. This one always catches me off guard. So let me check my hard copy and see where we are in relation to the rest of this. All right, so yeah, I am lagging. So let's take another problem. This time use hydrofluoric acid. It's a little bit stronger. Notice 10 to the minus 4th instead of 10 to the minus 10th. But it's still a weak acid. So calculate the pH of this solution, the weak acid HF. What are the major species? HF and water, because it's a weak acid. And then H plus and F minus are not major species. They're still involved in the equilibrium, of course, but they're not major species. Major species concept is to help us decide which is the controlling reaction for determining the pH of this solution. So we do a comparison. We've always got the water dissociation, and we've got this added HF at that given concentration. So we notice that this is 10 to the minus 4th versus 10 to the minus 14th, which is 10 orders of magnitude stronger. So HF dissociation is the controlling reaction. So now we set up the controlling reaction. HF plus water yields hydronium plus F minus. At the beginning, the concentration of HF is 0.5. And the hydronium and the fluoride ions are virtually zero. Right? We know they're not exactly zero, but for calculation purposes, we set them equal to zero. And then we know that the reaction, because there's zero or close to it, the reaction is moving to the right. That means we're going to lose some from this side and gain an X on that side and an X on that side. Why? Because the ratio of coefficients is 1 to 1. Now, what's the equilibrium situation? 0.5 minus X, HF, concentration of hydronium is X, concentration of fluoride ion is X. And if we're calculating the pH, this is a good choice of X, because once we find X, we know the hydrogen ion concentration, we can calculate the pH from that. So what's our expression in terms of the unknowns? Okay, so this is what it would be for the Ka expression, and then we plug in the values for unknowns, right? There's X in the numerator, right? XX, products, and then 0.5 minus X in the denominator. Well, as it turns out, 10 to the minus fourth gives us a value of X that is much, much smaller than 0.5. That's why we can ignore it for this calculation. So we drop the X from the denominator just so that we don't have to solve a quadratic. So now we got this expression equal to that value. We just take 0.5 times this number and take the square root of it, because it's X times X on this side squared, square root of both sides. And that's what this next expression is. Well, that's what you get. X is now equal to 1.897 times 10 to the minus 2. Now, do we do the 5% rule? Well, calculate pH at 1.72. Now, you don't want to do the 5% rule calculation using pH, because it's a log transformation, and it will skew the value, right? The calculation of 5% is a linear function, not a log function. So when you do the calculation, you have to use the actual value of hydrogen ion concentrations. So you would take this value, plug it back in here, here, and there, calculate the value and compare it to this value and see if it's within 5%. If it is, you're good to go. And that's what we've done on this page. We just plug those values in, right? 1.897 times 10 to the minus 2. Plug them in here, we get 7.481, and that is within 5%. In fact, it's only off by 3.9%. Now we could plug the values back in, like go back over here and put that value in right there, then calculate X, and you would get closer. That's successive approximations. The only other way to do it and get the exact number is solve the quadratic equation. But this is a whole lot simpler, and it gets you close enough. Okay, what do we mean by percent dissociation? When you talk about the acid here, it's a certain concentration. Actually, it's a concentration before equilibrium. So that concentration before equilibrium is some value of molarity, right? So it's like some molarity. What you determine is how much of that is dissociated, right? So if it's, say, 1 molar, and then you determine that you've lost, in the dissociation, you've lost 0.01 molar. That's the amount of this one that was dissociated. Against the original concentration, 0.01 divided by 1, right, times 100 is 1% dissociation. Correct? 100 times that, 1%. That's what we mean by percent dissociation. Now, the fact of the matter is, percent dissociation varies with the concentration of a weak acid. For strong acids, you're virtually 100% dissociation. You'll get this concentration and you'll produce you'll lose all of it, right? So this percent dissociation really has no meaning for strong acids or bases. For weak acids, yes, because you'll only get part of it dissociated. What has been observed is, for weak acids, this value, percent dissociation, increases as the acid becomes more dilute. That seems counterintuitive. You would expect higher dissociation the more acid you have. Well, it's kind of like that difference between the K equilibrium and the equilibrium position. The K for this acid is constant. It is constant. But if you change the concentration, then we can use that expression and that constant to determine what is the percent dissociation. And in fact, as we get weaker and weaker in the acid, more and more of it dissociates on a percentage basis. That's the key. You don't get more acid in solution as you decrease the concentration. You get more percent dissociation. So the acid concentration, the hydrogen ion concentration, as we get weaker and lower concentration of acid, that actually does decrease. But it doesn't decrease linearly, right? Let's see if I can draw that in terms of a graph, right? So if we say the concentration of the acid here and the percent dissociation here. Okay, so as the concentration decreases, we get more dissociation, right? So we do like this, and like that, and like that, and like that, and like that. Okay. So it's more like a curve, like that. So as the concentration, oh, no, that's wrong. Excuse me. No, that's entirely wrong. Because this is increasing. So it will be this. As we increase concentration, the percent dissociation increases. So it would be like this. Like that. Increased concentration, increased dissociation. It's a positive slope. But it's a continuously varying slope. Right? As you get more concentration, the percent dissociation, the increase in percent dissociation is less and less and less. Actually, it should be the other way around. That'll be like this. Higher and higher concentrations, the percent dissociation doesn't increase as much. All right. So, what does that mean for our pH? Well, what we're going to do is calculate the Ka for an acid based upon the percent dissociation. All right. So here we go. 8 molar formic acid. Formic acid is HCHO2. Formic acid is the simplest carboxylic acid. So it will be like this. Have a hydrogen here, like that, like that. That's the simplest carboxylic acid. There's a carboxyl group. There's your acid group. Oh, no, that's not right. This is the acid right here. That's the proton that dissociates. Okay. If you've ever been bitten by a fire ant, you know what formic acid is. That's a primary ingredient in the venom of a fire ant. In fact, the term formic comes from the Latin for ant. So the formic acid was I don't know if it was isolated from ants first. Maybe it was, but they were given credit. And the name was formic acid based upon its prevalence in biting insects like ants. Okay, let's get back to the problem. So calculate the Ka value for formic acid. All right, so we know that in our ice table, what we've got is this acid dissociating into that proton and that anion, conjugate base. Okay, initially we have 8 molar of this substance and none of this. So what is the change? Well, if we're going to lose 0.7% of this value, that's the change. We're losing 0.7%. So we multiply 0.0047, which is the decimal equivalent of the percent value, times 8. That's how much we lost. But that's also how much you gained of protons and conjugate base. Then we subtract this one from there. It gives us this value. This is the value for the equilibrium position for hydrogen ions and formate ion. Then you just plug it into the equation and calculate the K value. So there it is, 1.7 times 10 to the minus 4th. Based on this information, and all we need to know is percent dissociation, we can calculate the K value for that dissociation or acid dissociation in aqueous solution. So in that case, what is the pH? Well, we take the hydrogen ion concentration and we calculate it to be 1.42. Okay? So the value of Ka for a 4 molar formic acid solution should be what? It's a trick question. The Ka doesn't change. It should be exactly the same as the Ka for the 8 molar solution. But the percent ionization or the percent dissociation of the formic acid molecule at 4 molar will be greater than, it'll be higher than it was for the 8 molar. Let's see. I thought we were going to do a calculation for that. Maybe that'll come later. Yes. I think it will. In just a couple of slides. So for this weak acid, with the initial concentration of HA, and this is the dissociation, there's the Ka calculation. And we can say that, let's see. Well, based upon our ice table, we know that we're going to lose some X from our H0, so the equilibrium position is going to subtract whatever we've lost in the dissociation. Right? So HA is effectively HA0. And then X is equal to the proton concentration and the conjugate base concentration. Right? So that gives us, at equilibrium, we actually have a little bit of X, a little bit of X here for the hydrogen ions and the conjugate bases, divided by the initial concentration, because it didn't change that much. That's the only reason you can do that. This is that approximation step. So now that we have this expression for our K in terms of unknowns, what happens if you add water to the original concentration such that this concentration now becomes 1/10 of what it was before? Right? So what does that mean in terms of expressions, algebraic expressions? Right? Now we have these two values are a tenth of what they were. Right? We diluted them. And the new value of HA is a tenth of what that was. Right? This is the original divided by 10. Now that we've stressed the system by adding water, which way will the reaction proceed? Calculate Q, right? Right? So the Q for the new reaction, and this is before we reach equilibrium. We've stressed it by adding water. So now we're calculating the Q based on this 10-part dilution, 10-part dilution, 10-part dilution. And we have this expression now, once we factor out common elements, now we have x squared 1/10 times this value, which is Ka. Right? So if we know that the value of Q is a tenth of Ka, which way is it moving? If the Q is less than K, the system will move to the right. Right? Because if the Q is less than K, that means we've got not enough numerator and too much denominator. That makes it smaller than K. And if you've got too little numerator, that means too little product. So the shift is going to be to the right. What that does then is it increases the amount of product, which means more dissociation. That's an explanation for why the percent dissociation is higher for dilute solutions. The equilibrium position is shifted toward products. Even though the concentration is lower, the position is shifted toward product. All right. So the pH for 4 molar formic acid solution should be higher than the pH for 8 molar, which means more basic. Just because it dissociates more does not mean that we're producing more hydrogen ions. We're actually producing fewer hydrogen ions. We've already decreased the concentration by 10 times by adding water. Now, the hydrogen ion concentration is not cut by 10 because the shift will occur toward the right and produce more hydrogen ions to partially make up the difference. Right? So it's not a linear response. If you decrease the concentration of the acid by 10 by dilution, then you tend to cause more dissociation. And even though you have less concentration of hydrogen ions, it's not a tenth less. So let's look at what that means in terms of actual quantitative measure of the percent ionization. Okay, so if we start off with 4 molar formic acid, we have 0 this and 0 that. Then we lose some of this, we gain that in proper proportion, 1 to 1. Then we have this calculation, this is our equilibrium position. Plug that in the formula, do our approximation, X disappears here. Then we calculate the X, or the hydrogen ion concentration, at 2.665 times 10 to the minus 2. Now, what is that in terms of percent dissociation? Let's see, what was the original? Let's see. 3.76 times 10 to the minus 2. So the hydrogen ion concentration was higher for the 8 molar. Right? But calculate the percent dissociation. Well, in this case, this is how much of it was dissociated in molarity. This is how much you started with times 100. 0.67% versus 0.47%, which was given originally, right? So you do have more dissociation, except that the actual concentration of hydrogen ions has decreased. Okay, it seems counterintuitive, I know. But it's a fact. We just have to deal with it. Like I've said before, nature just does what it does, and we have to deal with it. So there's the pH, 1.57 versus 1.42 originally with the 8 molar solution. Okay, how about bases? Well, the Arrhenius base requires that the molecule contain an OH minus. The Bronsted-Lowry base simply has to be a proton acceptor. So here are some compounds that satisfy the Arrhenius base: lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide. And we can calculate the pH, the pOH of these solutions, and as a consequence, using our simplified version, calculate the pH also. So let's say we have 10 to the minus 3 molar sodium hydroxide. What's the pH? Well, ask yourself, is that a strong base or a weak base? If it's a strong base, then we don't have an equilibrium situation. We simply dissociate sodium hydroxide and calculate the pOH, then calculate the pH. So there's the pOH. pH would be 14 minus that, right? Which would be 11. Simple. About calcium hydroxide. Okay, you have to think about this. What is the pOH? The pOH is the negative log of the hydroxyl ion concentration. What does calcium do in solution? Calcium hydroxide. It completely dissociates into that and 2 of those. So if you have 10 to the minus 3rd molar here, how much of that are you going to have? 2 times 10 to the minus 3rd. Okay. Now the calculation becomes negative log of 2 times 10 to the minus 3rd, which is 2.7 pOH, and then pH is 11.3. Okay? Okay. Now let's look at, see, I'm getting my papers all wound up here. We're coming down the home stretch here, and we're going to talk about, okay, the equilibrium expression for the conjugate base of a weak acid, right? So the conjugate base of hydrocyanic acid is the cyanide ion. So the Kb for that reaction would be this, and I put that on the board earlier. So you react this with water and produces the acid plus the hydroxyl, and the expression is that, right? So if we want to calculate the pH for that reaction, we need to know what is the hydroxyl ion concentration, calculate the pOH, and subtract it from 14. So let's say we have, instead of hydrocyanic, we have ammonia. The Kb for ammonia is 1.8 times 10 to the minus 5. So what does that mean? That means ammonia in solution reacts with water, and it extracts a proton from the water molecule. And that's a mistake. That NH, that 4 should be a subscript. Let me make a note here. Here it is. I need to correct that. But that should be NH subscript 4 with a plus charge. So this Kb is written for that equation. And when you see the expression Kb for ammonia, you should automatically think ammonia reacts with water. And whatever that water, that reaction produces, goes into the Kb expression. Right? So there's the Kb expression for this reaction. Ammonia times hydroxyl divided ammonium times hydroxyl divided by ammonia. And since it's a weak base, the x is going to be very small, that change. So we can say x squared over 2 yields this value, and then we can solve for x, because that's the concentration, and there it is there. The OH concentration is this. The POH is 2.22, so the pH would be 11.78. All right? Very simple. And this expression here is derived from an ICE table. But the ICE tables for acid-base reactions, acid or base reactions, are very similar. They all look like that. That's why we didn't put the ICE table up there. It's redundant. It's repetitive and time-consuming. Now, I mentioned earlier polyprotic acids. The important thing to remember about polyprotic acids, those that have more than one proton to dissociate, they do so one proton at a time. And they'll give you a K value. So here's Ka1 for one dissociation. Then you have a second dissociation, and maybe even a third. For instance, if it's phosphoric acid, we'll give you 3 K values, one for each proton. The relationship of those K values is this. The first K value is greater than the second K value. It may not be a huge number, but it's always greater. And then the second one is greater than the third one. The reasoning being that if you say that dissociates to this, it's one way of thinking about it is purely electrostatic. If you try to remove a proton from a negative charge, is it going to be easier or harder than it is from a neutral? It's going to be harder to extract that proton from this negatively charged species. So the more negative the charge, the more difficult. So that means that this one and this one this is going to be easy, relatively, a little harder, even more hard to remove the proton. And in most cases, only the first dissociation constant controls the pH. For that matter, because after you take off one proton, then the rest of them are going to be much more difficult to remove. And that means they don't contribute much to the overall hydrogen ion concentration in solution. Here's an example, phosphoric acid. Notice that for the Ks, as you remove a successive proton, for the first one, it's 10 to the minus 3. For the second one, 10 minus 8. 5 orders of magnitude more difficult. For Ka3, 5 orders of magnitude more difficult than the second one. Right? So they're going to be less likely almost impossible to derive significant concentrations of hydrogen ions to affect the pH. This is the first dissociation right here. So that would be the K1, Ka1. And if your concentration is 1 molar, then the hydrogen ion concentration, we're doing the 5% rule. Okay, so let's go back. What we discovered that is this value is much too large to make that assumption. 1 minus x. X is significant. Right? That's what this calculation tells us. The 5% rule says that we're not allowed to make that approximation. So if we do a successive approximation and use this value here, input into the x value for the denominator, then we can do another approximation. And if we do it that way, then we find that when we do the calculation for the 5% rule, we find now we're less than 1%. So with that extra approximation, we have met the 5% rule and then some. So that means that the pH of this solution is going to be 1.08 at 1 molar concentration. So while the pH is not affected very seriously by the second and third dissociation, they do still operate. Those equilibria are still there and working. And it may be instructive from time to time to learn what is the concentration of the conjugate bases for each of these steps, right? The conjugate base for the first one is H2PO4 minus. The conjugate base for the second one is HPO4 2 minus. And the conjugate base for the third one is PO4 3 minus. And that's the one that we're questioning here. At equilibrium, what is the concentration of that PO4 3 minus? So first things we have to do, we have to go step by step, right? We did the first one at 1 molar, and now this becomes the beginning concentration for the second equilibrium. Okay. Now this also demonstrates that the X, or the hydrogen ion concentration, is not affected by the second and third equilibrium. Right. So we do the third one, and we find out that the concentration of the hydrogen ions is virtually the same. And then we input those into the equilibrium expression, right? The hydrogen ions, the HPO4 2 minus, which came from the previous determination. And then we solve for the PO4 3 minus. And we find that at equilibrium, look how much PO4 3 minus there is. Not much at all. So how could we increase the PO4 3 minus? Well, you can't do it from just dissolving phosphoric acid. What you have to do is couple it with a reaction that will extract protons with a much stronger base. Then you can remove protons, effectively driving the reaction to the end and making PO4 3 minus. That's the only way you can do it. Okay, so when we get an acid-base reaction, put it together. So now, instead of just dissolving an acid or a base in water, we're going to react a base of a given concentration with an acid of a given concentration And for our purposes here, we're going to stick to Arrhenius bases, right? Hydroxyl producers, hydrogen ion producers. Whenever you do it that way, you always get the same reaction. You produce a salt, which is the definition of a salt, which is the cation from the base plus the anion from the acid yields a salt. And then the other product is always water. So, can we do a qualitative prediction or a semi-quantitative prediction of what to expect if you react first a strong base with a strong acid? If you react a strong base with a strong acid, notice that all of this is consumed with all of that, and if they're stoichiometric, that is equal amounts, then you produce nothing but salt and water. So then what reaction determines the pH? The dissociation of water only, right? There's none of this left. So in that case, that reaction will produce a neutral solution. Strong acids, strong bases always produce neutral solutions. And the salts. What if you have a strong base and a weak acid? So let's do it this way. So we have a base, we have acid, and we have the solution that results from that combination. Okay, if they're both strong, let's say pH. If they're both strong, we have a pH of 7, neutral. If you have a strong base and a weak acid, you have greater than 7, or a basic solution. Right? So this is like rule of thumb. If it's a strong base and a weak acid, you get a basic solution. If it's a weak base and a strong acid, then you get an acidic solution. Okay? So what's the other possibility? Weak, weak. If you have a weak acid and a weak base, the solution pH is variable. And it all depends on which one is the stronger. Right? If this is a stronger base than that one is, it'll be basic. If this is a stronger acid than that one is, it'll be acidic. So that's the rule of thumb. Now, we need to understand why that happens. Okay? So for this last one, these first ones, of course, they're easy to understand. But for the last one, what you need to consider is the difference between the Ka and the Kb for the values. Right. The Ka for this one and the Kb for this one. If the Kb wins, then you get a basic solution. If the Ka wins in size, magnitude, then you get an acidic solution. Okay, so this is a qualitative prediction. I just put that up on the board. So let's say we have these two acids, weak acids, and before we do any combinations, Let's calculate the Kb, so we'll be ready. Right? So what's the Kb for the acetate ion? Right? Kw equals Ka times Kb. We showed that earlier. And the Kb is 5.6 for this ion. For the other one, the Kb is 1.6 times 10 to the minus 5. Okay, so now we have those values. We have the Kas and the Kbs. Let's see. All right. So if we were to combine, if we were to make a solution out of, let's see. No, that's not a good choice. We're doing these calculations for the next page, I think. Yeah, there's cyanide, and no, there's no. So why did we do that calculation? Just for an exercise, I guess. Before we go to the next slide, I want to explain why a strong base and a weak acid makes a basic solution. The tendency is to assume that the basicity of the solution is based upon the strong base. It's not. If you have a salt that's formed from strong base, weak acid, for example, sodium, let's see, I was getting weak. Sodium acetate. Okay? So what happens when you put that in solution? It breaks apart into these two. All right? That's not working well either. Let's try another one. So, what is sodium going to do in solution? Will it react with anything? No. I mean, it's not going to react here, right? Because it's completely soluble. So sodium will not react. It's a spectator. What happens is acetate. So where did acetate, what is it derived from? Acetic acid? A weak acid means this is a strong base. So now the reaction is going to be this base plus water. Which side is it going for? Product. If it's a strong base, it's going to extract a proton from that. It's going to make this plus that. That's where the basic nature of the solution comes from. Not from the strong base, but from the weak acid conjugate base. Produces the basic conditions. Okay? That's why when you have a salt that's formed from two weak acids, it depends on the relationship of the Ka and the Kb to each other. All right. That concept is probably not going to make a whole lot of sense until you work problems. So over the spring break, you'll be working some of these problems, and just look at the review document that I've placed in Blackboard, and it'll give you plenty of practice. And then, of course, the worked problems in my handwriting will help to explain, if you get stuck, why the procedure for solving the problem is the way it is. All right. So next, the question is, if you have 1 molar solution of each one of these compounds, arrange them in order of lowest to highest pH, like most acidic to most basic, lowest to highest pH. We can take 2 approaches. We can look at these in qualitative form and arrange them. The way I would do it was I'd identify the highest pH and the lowest pH, and then come back and try to figure out where the others are arranged. Right? So, are there any compounds in here composed of ions from strong acid, strong base interactions? Well, actually, I'm not doing just highest, lowest, I'm doing the middle, right? If we can identify strong acid, strong base interactions, we can say, this is neutral. It's right in the middle, right? So from lowest to highest pH. So this is lowest pH, 1, 7, 14. Lowest to highest. Are there any in here that are formed from strong acids, strong bases? Well, let's see. And we're talking about salts. Sodium chloride, sodium hydroxide, hydrochloric acid, strong base, strong acid. So sodium chloride would have a pH in the middle, right in the middle. Right? So we can mark that one off. Okay? Next, are there any strong or moderately strong bases? Right? They will be this way. Well, as it turns out, sodium hydroxide is. It's a strong base. Would have the highest pH. So we have sodium hydroxide. I'm going to stick it way out here. So that takes care of sodium hydroxide. The next highest pH will be ammonia, right? Why? Because we don't find any, that's an acid, that's an acid, that's an acid, that's a salt, that's a salt. So it's going to be modified base acid interaction, whereas this is a pure base. So even though it's a weak base, it's a stronger base than any of the others, right? So it's not that strong, but it's just underneath. So ammonia goes here, okay? So this would be higher pH than this. All right, so we got rid of ammonia and we got rid of sodium hydroxide. Now what's next? Are there any compounds composed of ions from weak acid, strong base, which makes a basic solution? Let's see, weak acid. Okay, there's a weak acid derivation, hydrocyanic acid, and a strong base, sodium. All right, so that would be a candidate for the next. That's going to be a basic pH, but it's not going to be as basic as these two. But it'll be more basic than the neutral, right? So we're putting them in order. Are there any acids derived from halogens? Any derived from halogens, except for fluorine, are going to be strong acids. As it turns out, yes, HBr is the strongest. So it'd be the lowest pH. HF is a weak acid, but it's still just a little bit more basic than HBr. So we can put a HF just here, right? So what does that leave us? Now we have to decide the relative positions of HCN and NH4Cl. HCN is a weak acid. It yields a higher pH than either HBr or HF. That's true. While the ammonium chloride is a salt of a weak acid and a weak base and a strong acid. This will likely push the pH closer to the basic than the HCN, simply because you're combining a base and an acid, whereas HCN is a pure acid. So logic would put HCN here and ammonium chloride there. Okay, that's the qualitative, semi-quantitative approach, right? To putting those in order of pH. The quantitative approach compares the Kas and the Kbs. On the acid side, we will put them in order of Kas, right? So the strong acid doesn't have a Ka. HF is the next, 10 to the minus 4, then 10 to the minus 10, 6.2, and 5.6 means that we were right. HCN is a little bit stronger acid than ammonium chloride, than the neutral, but the Bs are going to be, on the other side, would be in order 1.6 sodium cyanide, and ammonia is a little bit stronger base with a Kb. So we did put them in the right order, but this is how you would do it quantitatively, using the Ks. The Kas in order on the acid side, and the Kbs in order on the base side. All right. So let's see, where are we going with this one? We're getting there. I'm already a half hour over, so what's a few more minutes? Suppose we have a 0.3 molar solution of sodium fluoride. The Ka for hydrofluoric acid is 7.2 times 10 to the minus 4. Those are given. What are the major species? Well, if you put sodium fluoride in water, what's going to happen? It's going to completely dissociate, correct? So you'll have sodium ions, fluoride ions, and water, of course. And we just drew the Ka in here so that we would have it ready, right? Because we know the Ka for hydrofluoric acid, we just write this expression. We may need it, we may not. We'll see. Major species are this. So what possible reactions could occur with these species? Well, you could get fluorine, the fluoride ion, with water, right? Remember, HF is a weak acid, so it makes a strong base. So this is a valid reaction. The fluoride ions extract a proton from water and produce HF plus OH minus. You get water self-ionization. That's a possibility. What happens to sodium? Is sodium going to react with water? No. Sodium doesn't want hydroxyls, and definitely doesn't want protons because it's positive also. So that reaction and this reaction won't occur because sodium fluoride was completely dissociated, right? So 3 and 4 are just ludicrous. The only two we have to compare are 1 and 2 reactions in this list. So how do we decide? Well, this reaction has what as a Kb? The Kb is Kw divided by Ka. Right, we know that. So the Kb for this reaction is 1.39 times 10 to the 11th. It's going to be mostly to the left, but how does it compare to the K for water? Well, water is 10 to the minus 14th. this reaction. So this reaction is 3 orders of magnitude stronger, which means the controlling reaction for this comparison is the fluoride ion, right? We didn't go any further than that, but that says that this one, compared to Kw for water, which is 10 to the minus 14th, says that this reaction is controlling. So when you put it in water like this, this is not the actual reaction that determines the pH, right? It's the fluoride ion, which is this one. That's the controlling reaction right there for the pH. So we would set up an ice table with this reaction, not the acid reaction. Okay, so let's look at another possibility. Suppose we have a 0.75 molar aqueous solution of sodium cyanide. The Ka for HCN is 6.2 times 10 to the minus 10th, which means it's a weak acid. So what does that mean for the cyanide ion? That means the cyanide ion is a strong base because it's derived from a weak acid. What are the major species? When you put, let's see, when you put sodium cyanide in water, it dissociates completely. All sodium salts are soluble. So it makes sodium ions, cyanide ions, and you have water. And again, we eliminate the obvious wild goose chases, and we focus on these two because they are the only meaningful reactions. Then we compare the K values for each reaction. Right? So the Kb for this first reaction now is going, well, let's see. Yes, the Kb for the first reaction is 10 to the minus 5 versus for water 10 to the minus 14. Now we know that the cyanide reaction is the controlling reaction. That's why we use this reaction. Cyanide ion plus water yields HCN plus OH minus. We start off with 0.75 molar because sodium cyanide at 0.75 produces 1 sodium and 1 cyanide for each dissociation. And then we set up our ice table. Say this is the reaction, and we say, all right, with a value this small, X is probably going to be insignificant. That's why we estimate this value. And we find that the X is 3.46 times 10 to the minus 3rd molar. Calculate the POH because X is OH minus concentration. So that's POH. pH is that subtracted from 14. Okay. You can do the 5% test for this one, but I guarantee it's going to meet that test. Okay. So let's look at some of the theory behind acid-base activities. What 2 factors control the acidity or the basicity of a solution? Depends on the molecule. Right? 2 factors operate. What is the polarity of the bond? If you want a strong acid, then the polarity of the bond needs to be high. For instance, try another one. For that bond, hydrochloric acid, H and Cl, chlorine is much, much more electronegative than hydrogen. So the polarity of the bond is like that. That means most of the electron density is spent, its time is spent around the chlorine. Okay. So that gives you a positive dipole toward the hydrogen, a negative dipole toward the chlorine. All right, so when you put that in water, the hydration energy of the water molecules attaching themselves to each of these is easier to break the bond. Right, because the electron density is not in the bond itself as much as it could be. Right, it's spent more over here and that, so it's easier to break them apart. That's bond polarity. Now, that argument doesn't work for this one. The bond polarity might be like that, but this is a strong acid and this is a weak acid. So why, if the bond polarity here is actually, it's more polar, right? Fluorine is the most electronegative element in the periodic table. So why is this not a strong acid? The reason is bond strength. Bond polarity is not the whole story. The bond strength of this is greater. Than this one. So, and the reason for that is, once you separate the charges far enough, you start getting electrostatic attraction. And the electrostatic attraction overcomes the solvation energy to pull them apart in aqueous solution. So you have to consider these two. What's the polarity of the bond? High is good. Bond strength, low is good. All right. So here we find that the bond strength for HI is low. These are all halogen acids. HF, HCl, HBr, HI. Right? They're in the same group. So we can compare them. Compare apples and apples. The bond strength here for HI is low compared to the others. It gradually increases as you go up. Right? So we can still dissociate these three completely, but the bond strength by the time you get to HF is just too much. It's too high. In which case, HF becomes a weak acid as a consequence. Okay. Now, we're going to discuss different types of acids and bases. All right. Oxyacids. What does that mean? The oxyacid is one in which you have some species here, some element there, bound to oxygen, one or more oxygens actually, and the hydrogen is bound to the oxygen. So, what can we say about a series of oxyacids in which the only difference between in that series is the number of oxygens? Perfect example. There we go. This is perchloric acid, chloric acid, chlorous acid, hypochlorous acid. Which one is the strongest acid in this group? Here. acid strength increases as you increase the number of oxygens in the anion. Why is that? Well, here's what happens. Let's take this one. Let's see, one like that. 2, 4, 6, 8. Okay. So notice what happens. I'm trying to remember the correct terminology for this, and it escapes me for the moment. What's happening is we're looking at the bond between this oxygen and this hydrogen right here. If we can weaken that bond, we get a stronger acid. But if the bond increases in strength, we get a weaker acid. So how do you do that? Well, if you notice that the electronegativity difference between oxygen and hydrogen is significant, so it's a polar bond. But the chlorine is even more electronegative than the oxygens. So we get a shift that way, which is also pulling on electron density. And then we get a draw this way and that way, which further pulls on electron density away from the hydrogen. So if we add another oxygen out here for this, the pull is even stronger, weakening this bond. So the more you weaken that bond, the stronger the acid. And that occurs with more oxygens, right? The only difference in this series is the number of oxygens. Right? So this is going to be the weakest acid, stronger, stronger, stronger still, as you increase the number of oxygens. Okay, so that's the trend for oxyacids. And there are other series that we could talk about, but for now, that's that illustrates the point. So here you have, and here's the quantitative value, right? Perchloric acid is a very strong acid. Chloric acid is a strong acid, but it's not as strong as perchloric. And then you get chlorous acid and hypochlorous acid are weak acids. You can do the same thing with the sulfate versus the sulfite ion, the nitrate versus the nitrite ion. Okay, so what if we compare oxyacids, and the only difference now is the halogen, or this group, this X group. So if these are all the same, the OHs, and this H is the dissociated one, the proton, then the electronegativity of chloride is 3, bromide is 2.8, iodine is 2.5. And as you decrease the electronegativity of these things, you get a weaker and weaker acid. In fact, when you get down to this one, CH3OH is what? Methanol, wood alcohol, you know, the one that makes you blind if you drink it. And the electronegativity of this group is estimated at, well, we're using carbon here. Carbon is 2.3. So that's an extremely weak acid. You didn't think alcohols could be acidic, do you? Well, yeah, they're weak acids, but they can be, we can write an equilibrium expression for an alcohol in terms of the dissociation of its proton, and it doesn't dissociate very well. Let's put it that way. All right. Why did we leave HOF out of this series, right? There's chlorine, bromine, iodine. Why didn't we put HOF up there? Well, as it turns out, HOF in water is completely ripped apart, and it forms hydrofluoric acid plus hydrogen peroxide, right? So that reaction negates any measurement of Ka for that particular oxyacid, HOF. It just doesn't survive. All right. So we've got some other types of compounds that we're looking at in terms of what happens to them when we dissolve them in water. What happens to the pH of the solution when we dissolve these compounds in water? Well, these acid anhydrides, they say, and anhydride just means that water has been removed. Which is an indicator of what happens when you put them back in water. Right? If you remove water to make the compound and you put them back in water, then they're going to rehydrate. And that's what happens. And they're always formed from oxides of nonmetals. Sulfur, nitrogen, carbon, these are examples. So what happens when you put them in water? Well, what they tend to do is they combine the water into their matrix. And in this case, sulfur dioxide combined with water becomes sulfurous acid. Right? So what does that mean? That means that you're making an acidic solution. So acidic oxides are always made from nonmetals, oxides. And when you put them in solution, they make acidic solutions. They might be weak acids. In fact, all of these are weak acids when you put them in solution. So what's the other possibility? Well, metal oxides. How about those? Those are basic oxides. They're always formed from oxides of metals. So potassium oxide, calcium oxide, magnesium oxide, aluminum oxide. What are some others? Sodium oxide, lithium oxide. All of those metallic oxides, when you put them in solution, they produce bases by this reaction. So the oxide combines with water and produces the hydroxide, which further dissociates into a basic solution. So the basic oxides are formed from metal oxides, and they make the basic anhydrides, and they're called anhydrides for the same reason. You subtract water from this compound and you get this compound. When you put it back in water, then they rehydrate and they form the basic compounds. Those are always metal oxides, whereas the acid oxides or the acid anhydrides are formed from non-metal oxides. All right, now I promised we were going to talk about Lewis acids and Lewis bases. The Arrhenius base, remember, produces a proton, produces a hydroxyl. Lewis, the Bronsted-Lowry bases and acids, the acid of that type donates a proton or accepts a proton for bases. The Lewis acid base concept is not based upon protons, but upon electron pairs. So a Lewis acid is an electron pair acceptor. So what does that mean in terms of the other types of acids? If you have this, and it forms that, how do we justify that as a Lewis acid? Well, look at the bond. How many electrons are in that bond? 2. Right? All single bonds, all lines, are 2 electrons. So when we break apart, where do those electrons go? They go here. And they make this chloride ion, and they make that proton. Right? So this is an acid because electron pair transferred. The electron pair acceptor is this. The Lewis base would be the other way around. Say this one. So what's holding those two together? Well, it's primarily electrostatic charge. But the electrons go this way. This becomes a positive, that's a negative. So this electron pair donor makes it a base. The advantage of the Lewis concept of acids and bases is that it's particularly useful in non-aqueous solutions and organic chemical reactions. So we can react this aluminum 3+ ion with water, and the aluminum is a Lewis acid because it's a electron pair acceptor, and the water is a Lewis base because it's the electron pair donor. And when it does that, it forms this bond, right? That's the donor, there's the acceptor, forms the bond. In this case, it's also useful in coordination chemistry, where you have, in this particular case, water molecules associating themselves with aluminum, actually 6 of them, congregate around aluminum and donate their electrons to aluminum so that we form this complex ion, 3+ charge. Okay. So this is a summary of the 3 models of acids and bases. You can use that as a reminder. So this is just a summation of how you deal with acid-base equilibrium. What are the major species? Then what are the reactions involved with those major species? Eliminate the ones that make no sense at all. Then you find out which one dominates the solution. And that's the one you use in your ice table. And you do that by comparing the equilibrium constants, right? Which one is the stronger one? And then you do the calculations just like you would any other equilibrium. All right, that's my chapter 14, your chapter 16.